I'm looking at problem 4. The function is f of x equals x minus a times square root of x. That's my family of functions that I'm thinking about. I like to write my function formula to include a subscript in the function name. Now, that's not required. You don't have to do that, but I like to do it to remind myself that these functions do involve an unknown constant a. But when I think about this function, I just pretend a is a constant. I've said this before, I'll say it again. Whether a letter like this a represents a constant or a variable is all in your head. It's all in the way you're conceptualizing it, that you're thinking about it. I am thinking of a as a constant when I use calculus here. But in the end, what's more interesting is to ask what happens if I use different constant. What if a is some other number? What if a changes? So even though I do the analysis pretending a is constant, in the end, I'm interested in knowing what happens as a changes. A very, very useful kind of way of thinking about things for lots of applications, including our inventory management problem. So as always, take the derivative. Find critical points. Figure out if those critical points are mins or maxes. Maybe we also want to see if there are any inflection points as well. Maybe there will be, maybe there won't be. For the purpose of taking a derivative, I will write square root as 1/2 power. So the derivative is 1 minus, bring that 1/2 down, 1/2 a x to the negative 1/2 power, which you also could write as 1 minus a over 2 square root of x. It's an a there. If I set this equal to 0, I can try to solve for x. I get 1 equals a over 2 square root of x. I can square both sides. By the way, I should have done this in the previous problem, but I didn't. When you square both sides of an equation and still solve after that point, you really should check to make sure that the answers you get really are still solutions to the original problems, because squaring both sides of an equation can introduce what are called extraneous or fictitious solutions to the original. They solve the squared equation, but they don't solve the original. The reason that can happen is because squaring is not a one-to-one operation. That's the reason that can happen. I'm pretty sure in the previous problem we did, it wasn't a problem. So I squared both sides here, solve for x, 1 squared equals 1. Cross multiply, this means 4x equals a squared. So x is a squared divided by 4. I am thinking ultimately here about positive values of a, but I could think about this with negative values of a too. This is the x coordinate for any fixed value of a of the critical point. And right away I can see that if the critical point, if a increased, the fact that this critical point is a squared over 4 would mean as a increases through positive values, this critical point's got to move to the right. How does a critical point move? Because it's a different function. The function itself is changing as a changes. Is it a max or a min? I could try using the second derivative to figure that out. Maybe I could also use the second derivative to figure out if there's any inflection points or not. And if there are, where are they? Now differentiate that. The 1 differentiates to 0. Continue differentiating. It looks like we get this. Minus signs cancel. If you simplify this, you get a over 4x to the positive 3/2, which is, if you prefer, a over 4x times square root of x. That's the second derivative, if I've not made a mistake. If x is positive, which it would have to be for the second derivative to exist, It's never zero. It's always positive. This is positive if A is positive and X is positive, which is what we're assuming in these things. It's not going to change sign. There are going to be no inflection points. The graph, in fact, is always going to be concave up. And it doesn't matter what A is as long as it's positive. So we're going to get some sort of concave up graph, no matter what positive value of A we have. And in fact, that's going to mean this is always going to be a minimum. Second derivative test. The local min, it's actually even a global min because that's always positive. If A were negative, then the second derivative will always be negative and you'd always have a concave down graph. And that would always be a local max. I can already see in my mind's eye what the graph looks like this, like a smile. It does have, I was initially going to say maybe it has a vertical asymptote of 0, but it doesn't actually. F of 0 is 0. No vertical asymptote. But a vertical tangent line at 0, the F prime of 0 is undefined. Actually, this equation doesn't prove this because this equation assumed X is positive to begin with. But it's hinting that the derivative graph might have a vertical asymptote at 0. F prime of 0 is undefined. What's the y coordinate of the critical point? Maybe you'd be interested in finding that. Here's the x coordinate. To figure out the y coordinate, plug that back into the original function, right? We're interested in the original function. The derivatives just tell us about the original function. Plug that back in the original function. What is f sub a of a squared over 4? Using the formula for f, it's a squared over 4 minus a times the square root of a squared over 4. When you write a square root symbol by itself, it means the positive square root, though I do have a minus sign there. So I just take the positive square root, I get a over 2. Looks like this is a squared over 4 minus a squared over 2, which if you get a common denominator of 4 is a squared over 4 minus 2a squared over 4, negative a squared over 4. The y coordinate of the local min is the opposite of the x coordinate. That doesn't usually happen. That's pretty interesting. And actually it helps me graph it. So now if I draw a generic graph of this function, it's helpful to note that the critical point has a y coordinate that's its opposite, because what that will mean is that the low point of the graph will be on the line y equals negative x, where y has the opposite value as x. No matter what a is, your critical point is going to be on that line. Is that cool? And yes, f of 0 is 0. No matter what a is, 0 minus a times square root of 0 is 0. The graph definitely goes through the origin. Like I hinted at, there's a vertical tangent there. It's an infinite slope as you approach the origin. And the low point has got to be on this line somewhere before you go back up again. There is a generic graph. This point has to have coordinates a squared over 4 comma negative a squared over 4. Can I figure out anything else? I could figure out maybe where this x-intercept is. X minus a times square root of x equaling 0 means x equals a square root of x. Square both sides, x squared equals ax, which is the equivalent to this, which you can factor an x out of. It looks like the other x-intercept is at x equals a. That makes sense, though. I'm wondering if there's a mistake. Because not for every value of A would A squared over 4 be less than A. What did I maybe do wrong? Oh, this is an A. Oh, so I forgot to square this A. That's not an A, it's an A squared. That makes me feel better. Which means also this graph's not to scale. Because that number is supposed to be 4 times bigger than that number, which is not drawn that way. I could then use that information to try to draw it more accurately. The x-intercept should be 4 times further away from the origin than the location of the local min, which is also a global min. That would help me draw it more accurately. I could also draw it for any particular value of A, but the shape's always going to look the same. It's just going to expand, so to speak, as A gets bigger. That critical point will move downward as A gets bigger.